Welcome, everyone. Let's get started. Today, we are taking a major step in our MLOps journey. We will explore how to transition from manual, click-driven deployments to fully automated resource provisioning and model training using GitHub Actions. By the end of this session, you will know how to build secure, scalable infrastructure as code pipelines for your machine learning workflows. Let's begin with the fundamentals. What is GitHub Actions, and why do we use it in machine learning operations, or MLOps? GitHub Actions is an automation platform built directly into your source control repository. Traditionally, a data scientist might manually provision a compute cluster and manually click train in a portal. This manual approach is slow, error-prone, and nearly impossible to audit. By using GitHub Actions, we write declarative YAML code to automate these tasks. This means the exact same steps are followed every single time. It provides rapid development and reliable delivery of your ML artifacts. By integrating this automation, we perfectly bridge the gap between experimental model development and robust, scalable production deployment. Take a look at this high-level flowchart. It illustrates the automated MLOps paradigm. On the left, our data scientist pushes updated code to the GitHub repository. This push event instantly triggers GitHub Actions. Notice how GitHub Actions forks into two automated paths. First, it provisions the necessary cloud resources, like compute clusters, and second, it submits the model training job. All of this orchestration happens automatically within the Azure ML workspace without a single manual click. Before we write a single line of automation code, we must secure our pipeline. A critical mistake teams make is using a personal user account for automation. If that person leaves the company or their password is compromised, your entire infrastructure is at risk. Instead, we use service principals. A service principal is essentially a secure identity created specifically for an application or a workflow. To connect GitHub to Azure, we generate a service principal using the Azure CLI and assign it strict, least privilege permissions to our Azure ML workspace. We then take the resulting credentials and lock them away as encrypted GitHub secrets. When your workflow runs, it pulls these secrets, authenticates securely with Azure behind the scenes, and executes the deployment safely. This sequence diagram breaks down the highly secure authentication handshake. When the GitHub action starts, it reaches into GitHub secrets to retrieve our stored service principal credentials. It passes these to Azure Enter ID. Enter ID verifies the credentials and issues a secure, temporary token. Finally, GitHub Actions uses that token to communicate with the Azure ML workspace to provision resources and initiate the training job. Now, let's look at the blueprint of our automation, the YAML file. In GitHub, workflows are defined using YAML configuration files stored directly in your codebase. This file dictates three things: the triggers, defining when the pipeline should start, the jobs, grouping the workload, and the granular steps, defining the execution. Treating your infrastructure and deployment logic as version-controlled code is incredibly powerful. Inside these steps, you will instruct the runner to check out your repository code, log into Azure using your service principal secret, and install the Azure Machine Learning CLI. Once the CLI is ready, it triggers your resource provisioning and model training. When you are first building this file, always use the workflow dispatch trigger. This allows you to run the pipeline manually with a button click to test that everything is working perfectly before adding automated triggers. This flowchart maps the anatomy of our YAML file. At the top, the workflow is initiated by our manual workflow dispatch trigger. This drops us into the primary job. The job executes sequentially. Step 1 checks out our source code. Step 2 securely logs into Azure. Step 3 installs the required Azure ML CLI tools. Finally, Step 4 actually executes the machine learning job in the cloud. To maintain enterprise-grade stability, we must implement feature-based development. It is an absolute cardinal rule of MLOps that data scientists should never push code directly to the main production branch. To enforce this mechanically, we set up branch protection rules in GitHub. When a data scientist wants to update a model's hyperparameters, they must create an isolated feature branch and submit a pull request. This is where automation shines. We configure our YAML file with an on pull request trigger. The moment the PR is opened, GitHub Actions automatically provisions temporary compute and runs the training script to verify the new code doesn't crash. Once peer-reviewed and merged, an on push trigger can automatically deploy this newly validated model to the broader environment. This structure guarantees zero downtime from bad code. Let's visualize this workflow on a Git graph. The solid blue line is our main branch, the holy grail of our production code. The data scientist branches off to feature/tune model to safely test new hyperparameters. They commit their work and open a pull request. Once the PR passes our automated action checks and is manually approved, it merges back into the main line, triggering our final deployment workflows. As your machine learning projects scale, relying on a single workspace for everything becomes a critical risk. We must adopt environment segregation. We divide our MLOps lifecycle into development, staging, and production. Ideally, these are entirely separate Azure Machine Learning workspaces, each linked securely to different environments defined within GitHub. Why do we do this? Because a data scientist running a massive, experimental deep learning job should never consume the compute resources needed by your live production web app. Your GitHub Actions workflow handles this dynamically by pulling different variables and secrets, depending on the target environment. Crucially, the staging environment becomes your dedicated quality assurance zone. Here, integration tests simulate real-world traffic to validate the model's performance without exposing real users to any risk. Observe how the GitHub Actions workflow orchestrates across our architecture. It first deploys changes to the development workspace for isolated experimentation. Once tests pass, the workflow promotes the artifact to the staging workspace, which is explicitly built for quality assurance and integration testing. Finally, the automated pipeline pushes the fully verified model to the production workspace, where it safely handles live user traffic. Automation is incredibly powerful, but true enterprise MLOps requires a human in the loop. This is where gated approvals come in. A gated approval is a security checkpoint that pauses your GitHub Actions workflow until an authorized human explicitly signs off. Why is this necessary? Because while automated tests can check code syntax, a lead data scientist or business stakeholder needs to verify the model's actual business metrics before it goes live. We configure these gates inside GitHub environments. The workflow will automatically provision resources and test the model in staging. Then, it halts. It sends an alert to the required reviewers. Only after the reviewer analyzes the metrics and clicks approve will the pipeline resume and deploy the resources to the production environment. It is the ultimate safety net. This flow represents our gated deployment sequence. The workflow deploys the model to staging and runs automated quality assurance. Then, it hits the yellow diamond, the human approval gate. The entire pipeline pauses here. If the designated reviewer finds an issue, they reject it, halting the process and alerting the team. If the metrics look fantastic, they approve it, and the pipeline safely continues the deployment into production. Let's perform a deep dive on how infrastructure as code practically integrates with model training. GitHub Actions isn't just a code copying tool, it actively commands your cloud infrastructure. By applying IAC principles, our YAML workflow dynamically provisions the necessary compute clusters precisely when needed and spins them down when finished, radically optimizing cloud costs. How does this happen? Within our action steps, we use the Azure CLI command, azml job create. This command pushes your training script and simultaneously requests the specific compute configuration required. Crucially, while this training job runs on the newly provisioned Azure Compute, MFlow is running in the background. MFlow records all hyperparameters and metrics, creating an unbreakable, auditable link between the specific GitHub commit that triggered the action and the final model artifact produced. Look at how the components interact in this diagram. The GitHub Actions step executes the CLI command, sending instructions to the Azure ML control plane. The control plane dynamically provisions a compute cluster and pushes the training script to it. The cluster executes the training. At the end of the line, MFlow automatically captures the metrics and registers the model, creating a seamless, fully tracked infrastructure as code deployment. To tie all of this together, let's look at a real-world use case. Prosware, a healthcare startup, developed a diabetes classification model integrated into a web application for medical practitioners. The major challenge: medical data drifts over time. As patient demographics shift, model performance degrades, requiring constant updates. Manual updates are too slow and risky for healthcare. So, Prosware implemented this exact GitHub Actions MLOps strategy. Now, when data scientists identify drift, they tweak the algorithm in a feature branch. Merging their pull request automatically triggers the GitHub action. The workflow uses stored service principal secrets, provisions fresh compute in Azure ML, retrains the model on new data, and securely deploys the updated classification engine to the web app. The practitioners continuously receive highly accurate diagnostic insights, completely automatically. In our final diagram, we see the prosware lifecycle. It starts on the left when data drift is detected. The data scientist updates the code and merges the pull request. This instantly triggers the GitHub action. The action reaches into Azure, automatically provisions the required compute, and retrains the diabetes classification model. Once complete, it pushes the high-performing model straight to the live web app, solving the business problem elegantly and securely.